Okay.
All right, so our next speaker is Professor Mahony. He's a professor in the Research School of Engineering at the Australian National University. He received his Bachelor of Science in 1989 in Applied Mathematics and Geology, and his PhD in 1995 in Systems Engineering, both is gained from the Australian National University. He's a fellow of the Active League and was president of the Australian Robotics Association from 2008 to 2011. His research interests are nonlinear systems theory with applications in robotics and computer vision. He's well known for his work in aerial robotics, geometric servo design, matrix subspace optimization, and image-based visual servo control. And we're so glad to have him here today to talk to us. Thanks so much.
Thanks so much. What's the volume like? That okay? Fantastic. All right. So thank you very much for the invitation to come along and talk. I'm going to give a talk which has a little bit of history because I've been in this field for 20 years now, which is embarrassing to say, but nonetheless. And then I want to talk to you just about a symmetry, the Galilean space-time symmetry, which is one that we've been playing with lately, which is very exciting. So symmetry is really the essence of what we're doing. So I've been interested in state estimation for some years. And originally we got interested in estimating the state of aerial vehicles. And it was a major problem trying to actually get a robust estimator that was able to estimate for UAVs, the actual state estimator. The quality of the IMU was very poor at the time. Is that screen jumping in and out? Yeah. I can sort of see it through the edge there. Is there any way of...
I can switch to mine. I have your top slide up if you want.
If it's more reliable, I guess.
Okay, let's do that.
All right, what should I do then? I could just close this one.
Yeah, you should just be able to leave
you turn yours round.
Great.
Sorry about this.
No worries.
And my wonderful pointer is wasted.
We've got one here if you want to. Just pulling it up. Oh, I gotta put it in there.
A little bit more centrally. So
Thanks. There it is. We can do this one, share. Come on. Fortunately, we're ahead of schedule, so. Interesting.
Screen working? Screen is working.
Now it's Zoom that doesn't want to cooperate. Let's see if this works. Actually, let me put it onto.
Can see it in the phone, right?
Podium's not optimally placed for this activity. And the mouse is so small. There it is. Okay. Just be present. Thought we had all these things ironed out. Of course, that's how it goes. Slideshow. Okay, and then let's just see if Zoom will let us screen share the other thing. Stop share. And then if I come back to here. Okay. Oh, the challenge is that we don't have your slides on the screen that you can see. Let me just change this to mirror real quick.
So you have a clicker?
Yes, I do.
And stand in front.
Great, let's do that.
I'm cool with that.
Yeah, it's, oh shoot. Okay, see if the clicker works.
That works. Okay, so I can click, but what about volume?
Um,
I have a loud voice, everyone hears fine.
I could also give you the handheld remote if that's helpful. Up to you.
I can talk in a microphone if you want me to.
Okay.
All right. Where are we going? Fantastic. So we got into this question with aerial vehicles. And so we worked a little bit on attitude estimation. Then there was some work on velocity aided estimation, which has really been done. I did quite a bit of work on homography estimation and image registration. I'll talk quickly about that. Inertial navigation systems and virtual inertial odometry. And the argument I would make at this point in time is that in all of those fields where we really established the symmetry, the filters that have been developed in this way really are state-of-the-art filters. Perhaps in the visual inertial odometry, the jury is still out, but I would argue strongly that in all of the other cases, this approach really is the way to do things. And then there's a bunch of problems that we're looking at the moment: tracking control, epipolar geometry, range slam, rotating frame IMS, I'll talk about today, which is an active problem, a bit about target tracking, people are getting into control. So the essence of what makes this thing work is symmetry, right? So the original problem that we tackled was this top box here, which was attitude. And it was really the point where we said, you know, we're going to use the lead group symmetry to actually do what we needed to do. And of course, in that case, in attitude, that's what you accept, right? It's just SO3. So everyone knows about that. So it's very easy to get into and understand. And there was a bunch of work that came out of that you can read the slides afterwards. So there was this very nice piece of work by Bonneville and Martin in France, where they recognised that there was a symmetry group, which actually is almost like an SE3 symmetry. It developed into the extended co-symmetry SE23. And they looked at this velocity aided attitude in 2009 and really made some big steps in that. My own contribution in that field is quite recent, where we've done some observer design in that same area, but that's a really powerful symmetry. And that really led down to this inertial navigation systems. And that was Bonneville and Barou, in fact, were the ones that really did a lot of the good work in that area. And that's really the extended co-group. This SE23 was symmetry that made everything come together and work for that. And my own contribution in that was with Stefan Weiss and his students here, Alessandro Fonacia, where we actually looked at the tangent bundle of that as a way to model bias in the same problem, and that actually improves the performance a little bit. So there's some examples of what I'd say is standard Lie groups. But there's some other interesting stuff that we've been doing as well. So this top one, image rectification, where the state space that you're actually estimating, you're estimating an image. And in homography estimation, you're also estimating the normal to the actual plane, so a structure parameter or a scene parameter, and you're estimating the depth you are from the plane. So you estimate the homography, the normal to the plane that you're estimating, and the depth from the plane. So that's this state space at the top here. Which you can see images S2 and R+, and the symmetry that goes along with that is a special linear group, SO3 and multiplicative reals. And the action there is, so you've got a Lie group, which is direct product, and the action has this a compositional nature. We've got an image composed with a homography and then change the base point. So that's an interesting symmetry, and that's led to some very, very good homography estimation algorithms and image rectification. Oops, sorry. And then I'll also mention this visual inertial odometry problem at the bottom, where your state space that you're estimating is SE23. So this is the extended codes group. And you have a set of points in R3, which are points in the environment that you're trying to estimate. But you don't estimate them with Euclidean symmetry. Each one of these points, instead, you estimate with what I think of as a polar symmetry. So when you've got a point in space, instead of estimating its X, Y, Z coordinates, you estimate its direction and its range, and the symmetry is SO3, so you can move the direction by rotating the group, and you can change the range by multiplying by a scale factor. And you get significant advantages out of doing this. In fact, what you've done is you've created local coordinates and a global coordinate chart which is well adapted to the natural noise of the measurement systems. All right, so that's enough of sort of the history of where we are. What I want to talk about today is this rotating frame INS. And in particular, this question of, can we build an estimator using these symmetry ideas to solve the following problem? So I have a frame attached to the surface of the Earth. It's moving around with the Earth. Have an active agent with a frame B in space, and I want to estimate the rotation, the position, and the velocity of that frame with respect to my rotating frame. Okay? And this is a problem that there are a number of groups around the world looking at the moment, and it's a beautiful example of how to use Galilean symmetry. So the inputs you have a straton IMU for the active vehicles, so you have angular velocity and acceleration. You know the rotation of the Earth, omega, and you know gravity, where your base frame is. And so the way we're going to solve this is using Galilean symmetry. All right, so Galileo, back in 1600s, was studying celestial motion. And so he was interested in doing experiments in his workshop to understand the motion of bodies. And he knew, at that stage, he knew that the Earth was going around the sun. And he was really concerned that the fact that he was traveling very, very fast through space would actually change the way that physical laws work, and would actually mean that his experiments were not valid to infer what was going on in celestial bodies. And he came up with this principle of relativity, which essentially says that it's an analogy in the ship. So if you're inside a ship and the ship is moving at a constant speed, so long as there's no change in that uniform motion, you can do experiments in that ship and you will not be able to tell whether you're moving or not. And the reason he was interested is to say, I can do experiments about celestial motion in my workshop, and it will tell me something about what's actually going on in the real world. And this is the principle of relativity, which is sort of fundamental in relativity. So Newton picked up on this later and applied that in a physics sense to study the rate of change of momentum, essentially. So that's the principle he applied to then derive Newton's laws of motion, the Newton's second law of motion in particular. So everything stayed about the same until the mid-1850s, and then people started looking at electromagnetics, okay? And Maxwell's equations were there, and they were doing studies of electromagnetics, and they realized that the speed of light was finite, and that this screwed up the understanding of what Newton was doing. So around this time, there were two things that came about. One was that they knew the speed of light was constant, but they wanted this relativity. And Poincaré in 1904, they'd actually done a lot of the work. Lorentz had already done his work about the Lorentz transform and some of the other things that happen in physics. Poincaré actually wrote a paper where he really said, no, relativity still exists, right? So he really formalized relativity for a fixed observer, uniform movement of translation, the laws of physics phenomena are the same. And they knew that then you had to have something going on with the time axis and with constancy of time. And it was actually Einstein that came along, and it was similar to what Newton did. He said, okay, I've got the principles. We know what the principles are. Here's actually the physical laws that make everything make sense, right? And so he said, okay, the principle of light is constant. The speed of light is constant. That means that time changes, the way you measure space changes, et cetera, et cetera. So we don't need to go there. So Galilean symmetry says, what I'm going to do is assume that time exists independently, the principle of absolute time. So that tells me that if I synchronize a bunch of clocks all over the universe, they'll all stay in time with each other. And a consequence of that is that the speed of light is infinite, right? But if I send information anywhere in the universe, it gets it instantaneously. If you work in that space, which as roboticists, most of our things go slower than the speed of light, you have a beautiful symmetry. Time is universal, motion is indistinguishable up to the change of the inertial frame, and you get Galilean symmetry. So Galilean symmetry is something that looks like this. It essentially says that if I have two frames that I'm interested in, so frame B and frame B prime, and I'm going to measure them with respect to some other frame. And if frame B, which has coordinates R, B, and PT with respect to frame A, if it is inertial and I apply a Galilean symmetry of this nature, then frame B prime will be inertial as well. So a Galilean symmetry is on the top right here, a rotation. So you rotate your frame. The third line down is the transformation of position. So it's like a rigid body transformation, QP plus X, plus you allow a little bit of velocity to change as well. So your velocity changes as the rotated velocity plus a u. Your position changes with a plus TU. You can see that here. The rigid body transformation will take you there, and then it's being translated for t seconds, so the position changes. And you can also track for time, and you can change the time. So that's basically the full symmetry of Galilean space-time. So there are a set of homogeneous coordinates for Galilean space-time. So remember I said I'm representing the position of a frame by rotation, a velocity, a position, and a time. So I can write those in matrix form, and it looks like an S3 matrix. It's a little bit bigger than an S3 matrix because it's got these second rows. If you delete the column, second row, you'll get back RP01. And then you have this V, which couples with the time. So this V and the time will couple in the matrix multiplication. And so then you get this beautiful realization of Galilean symmetry, where if I could take my Q, U, X, and delta, put it into the same matrix structure, then the actual transformation of Galilean space-time is the same as transformation of matrix multiplication. And it's entirely analogous with rigid body, most of you all know and love from our fourth-year robotics texts. All right. Tied up inside this is the concept of space-time. So when I write down a position now, I write down homogeneous coordinates. So I have a P, I have a 1, but I also have the time that event occurred. So when I write down PT1, I mean there was something at the point P in space at the time T in space. And when I transform it with the Galilean transformation, you can see I change the time and I change the position that it was in. So very beautiful. So I've talked about the symmetry and I've talked about homogeneous coordinates. And what I'm doing here is the same trick we do in pose, where the fact that we can transform space. So here I have X, which is in this Galilean group. I can transform space to any other frame, and that allows me to write coordinates to any other frame as a transformation of an identity element. So what I do is store relative. So I have a frame A, and there's no coordinates. So I say, okay, imagine my observer is at A. I assign the identity coordinates to A, and then I can assign coordinates to any other frame I'm interested in by applying the transformation X from the Galilean group. So I've now confounded the concept of coordinates of a frame and the transformation that takes you from the origin to that frame. And I'm just going to leave that confusion sitting there in the talk and use X for most of the calculations, which means I can apply all of the Lie group theory and then have it mean something in terms of physical variables and coordinates. That makes sense. All right, so the reason why Galilean symmetry is so cool is because it plays really nicely with inertial measurement units. Surprise, surprise. Quick question, yes?
Is the Galilean symmetry is a group?
Yes.
Okay.
Yeah. So that matrix group there, it's right triangular, it's a group. Yeah. Okay, preserved rotation. Same as in fact you can sort of see it when you just do this multiplication, right? So that's a group element. Yeah. So it plays really nicely with inertial measurement units. So if I have an inertial measurement unit sitting on B, and I'm measuring with respect to an inertial frame. So here's my flat Earth model, right? Sun going around the Earth. Here's Australia, my frame of reference in Canberra, where I live. What I measure is angular velocity omega and linear acceleration A. And the actual motion of these variables is given entirely by the angular velocity, the acceleration, kinematics, P dot equals V, which is a known sort of property of what's going on. And don't forget time, right? So time is absolute, so I know T dot is equal to 1. Now, the really cool thing about the Galilean group is it actually encodes all of that in a really natural way. So at the bottom right here, I've defined my group element, X, And I've defined an input matrix which has those measurements, which are inertial measurements, right? Omega and A, and don't forget time. And what you find is if you multiply out this relationship here, if I take the derivative of RVPT and I actually apply this as the as a left invariant vector field, what I get is exactly the inertial motion. And you can see how neat this is, right? So here I've got T dot. So T dot is going to be the 2 column by the third, and you can see it's a 1 here, multiplies that 1, you get your 1, which is P dot equals 1, and you get your kinematics. So P dot is this row times that column, which is V times 1, which gives you your V. So not only do you get your inputs, but you actually get the natural structure of Galilean space-time that comes out of this. So it's very, very cool. All right, so now I'm going to use this to model rotating frame Earth. Okay. So this is the problem that I set up at the start. So I've got my rotating frame A, and I've got my frame reference B that's moving around in space. What I'm interested in is the relative pose, right? So RVP. So I put that into a matrix that looks like a Galilean group. And what we see is that the time here is 0, which makes sense because this frame of reference on the Earth's frame, it's actually going at time t, right? So at time t, I've got this frame, at time t, I have that frame. The transformation between the two has no time on step, it has a 0 in that place. And this is the extended pose group, right? It's also called the isochronous Galilean group, and it captures Galilean transformations that don't have any time on step in them. All right, so that's the sort of structure, and this is this group that was so important in the VA model in the IEEE that we've been doing. So this is the object that I'm going to be studying, but the caveat is it's not between inertial frames, right? So from A to B, A is not inertial and B is not inertial. So all of that stuff that I talked about, how cool it was, doesn't work anymore. So if I take X and B, I take its derivative, I do not get this beautiful set of equations that I had before. And you can see this straight away. Firstly, you don't see the Earth's rotation, you don't see gravity. But one of the things you don't see either is that, I had a 0 here, so the time derivative after 1 over here that came from that other equation, and this doesn't make sense at all. This matrix equation is just wrong. So the answer, of course, is that you need to work with respect to inertial frames. So what we do is we introduce a third frame, which is going to be inertial. Doesn't matter whether it's absolute frame or anything, just an inertial frame. And I'm going to write down the coordinates of frame B and the coordinates of frame A with respect to this inertial frame. And things get really simple now. So from the inertial frame, I can write down its kinematics. And because I've got a strap on I and U, I know omega and I know A, so I can actually write this equation down that I just showed to you before, and I immediately get these equations on the right. Now, these aren't the equations of the relative pose. These are the inertial equations of an object flying in space. So it doesn't see gravity, doesn't see anything because it's just flying around. Okay? Gravity comes when you look at the reference frame. Okay, so I can do the same thing for the reference frame, from the inertial frame to the reference frame, and I'm sitting here on Earth, and that's not negative Earth rotation, it's actually Earth rotation, it's a typo. But centripetal acceleration is -2. So the I and U, in fact, this is the same thing that you would measure if you put an I and U on the ground at frame A. You'd measure the rotation of the Earth, and you'd measure the exogenous acceleration applied to the I and U to stop it falling into the Earth, applied on the surface of the Earth, of course. So again, I can just write down these equations at the bottom, and now I can see where the gravity is going to come in here, and where the Earth's rotation is coming. All right, so I've got coordinates for my reference frame, I've got coordinates for my active agent, I've got a velocity for the reference frame, W, I've got a velocity U for the active agent, and I have this N matrix, which is the 1, right? So what I've done is I've taken away the 1 from here, and I put it into matrix N. I use N because it's the that generated the nil-clothing group associated with kinematics. So this group, the twin form of this group is definitely degenerate, so be careful. So I have that N sitting in there. All right, and then it's just the same as any robotics test, right? And that's the cool thing. Once we set up this machinery, we can treat this problem like any robotics. So I'm going to go from A to B. So what I do is I go from A to 0, 0 to B, same as Mark Swan would have done. And A to 0 is the same thing as 0 to A to -1. And you just do the other. And it's really that easy. And inside those matrix multiplications, you're actually carrying around velocity in time. And it's beautiful, absolutely beautiful. So now if I want to work out the kinematics, I just take the derivative of that. So I'm taking the derivative of the inverse matrix and the derivative of an actual matrix. So when you take the derivative of the inverse, the velocity pops out on the left with a minus sign. Take the derivative of the actual matrix, velocity pops out on the right. And you get this set of equations here, which is absolutely gorgeous, very, very simple. It's a group affine system. And it's associated with this set of equations at the bottom. So this is the rotating group equations, and it has all of the symmetry properties that you would want. Very, very simple. Now, there's one thing that you've got to be really careful about here. I've built this up from physical principles, and in doing that, the velocity that I'm modeling is the inertial velocity of the system, not the coordinate velocity. Okay? In particular, this third equation, P dot does not equal V. It is V minus something which is associated with the fact that the rotating frame is spherical. Okay? And indeed, if you pick up a textbook, a physics textbook, and ask about what are the dynamics or linear dynamics of an object moving in a moving plane, you'll get this equation at the bottom, right? So P dot, imagine that's the velocity. So ddt of P dot, which is like the acceleration of the point. And so you substitute into the RA minus V cross V, okay? And you've got a P dot that comes from multiplying with omega is constant, so I just have a P dot here. Substitute again to get everything in terms of P dot, and you get back your virtual forces, Coriolis force and the centripetal force that turn up in textbooks, right? So by moving into the inertial representation, it simplifies the scenario a lot. And indeed, these equations don't have symmetry, and these equations do have symmetry. So you can study this as a left invariant system on a group affine system on the Galilean group. This does not have symmetry. Okay, you can't apply it with very easily. All right, now I don't have time to talk. I'm doing fine. I don't have time to talk about all of the high level stuff or all of the filtering theory. But the point is that where we are now with this is in the same position as I gave you in all of those intros. So we have a state space. In this case, we have a rotation, a velocity, a position. We don't need to estimate the time. So that's our state. And then our symmetry is the Galilean symmetry. And we have what we mean by that symmetry and have a group action, and we can apply the invariant filter. So, in conclusion, and I won't go through the details of the Galilean filter. I wanted to concentrate more on giving you the insight. In conclusion, Galilean symmetry is the natural symmetry to model rigid body systems moving in space. And I think that actually it's going to be a really powerful symmetry for the next few years, able to do quite a lot. And it really takes you from flat Earth to rotating. So, thank you very much.
You can start, Mike.
Yeah.
Maybe if you find one question. Anybody? Okay.
So to the case, which case?
The case of
Yes, okay. So the answer to that is yes. Effectively, by introducing the Galilean group, That's allowed us to deal with these rotating frames. But we already have a theory, which was the SE23 theory, which actually it was already known that you have this xn minus nx term. And so that actually acts as an automorphism on the extended pose group. So in fact, it's almost already there in the literature, right? There's a very beautiful INS paper that Alessandro sitting behind you wrote that actually does that uses the TSE3 and deals with biases. Yeah. So that theory is basically written already. Yeah.
And because I want to answer questions, to save the rest of the panel after again. So thanks so much, Rob, for joining us. I appreciate it.